Oh, in case you weren't here earlier when I showed this, on Canvas, I've put this. Oh shit, good job, John. I wonder if I could just do a whole thing and nobody would tell me. So on Canvas, I put the trig identities that you need to know, including some we haven't done yet. So I just figured now is a good time to put this up there because we've learned most of these. Yeah. So you go to Canvas, you'll see trig identities right here. Everything above this line, you have to memorize, you have to know. Everything below this line is still a good identity, you just don't have to memorize them. Why don't I make you memorize these? Because I don't have them memorized either, so I'm not going to make you do that. Okay. Is everybody with me? So this obviously looks familiar here, right? These we just learned yesterday, right? Cosine is a jerk, kind of stuff here, right? This is old news. This is good to have on here. The inverse trig stuff. This we just learned yesterday, right? There's that cosine squared minus sine squared. One right there. I know this is tiny, but I'm sorry, I can't blow it up anymore. We still don't know this one yet. We're going to learn that today. And of course, you got all this weird shit down here. Okay. I also put the Greek alphabet up there just in case anybody's curious. You do not have to memorize this or anything. You never have to look at it again except for right now. I just put it up there in case you were curious. Okay. So anything else? Homework? For general questions? Okay, so just to remind us, oh, sorry, go ahead. 12 from 91, okay. No, go away. Oh yeah, look at that. Well, first off, that's really weird looking. Is that supposed to be negative x in there?
It's the negative x.
Yeah, all right, I don't know why I decided to freak out. So my very first, so that's got a lot of stuff in a row on top, right? Two things. What is sine of negative x? Does anybody remember? Sine of negative x. Yeah, negative sine x. I love it. So do you see how if you replace sine of negative x with negative sine x, doesn't that just cancel with that negative?
Right.
So this just becomes sine x. Right? What is secant? 1 over cosine. You see how these cancel?
Okay.
Cosine times secant is 1 because secant is 1 over cosine. Is that cool?
Right.
So that should cancel. What is tangent? Sine over cosine. What's cosecant? 1 over sine. So you see how the sine on top and the sine on the bottom cancel there? So,
right.
Yeah. So this one's nice. A lot of stuff cancels. Right? So see, sine x times 1. Rewrite that as sine over cosine. Rewrite that as 1 over sine. Cancel some stuff.
Right.
Yeah. You get the idea?
Yeah.
Okay.
That's why I was like, what are we gonna do?
So that's the thing to realize. Three of the trig functions are reciprocals of the other 3, right? So what is tangent times cotangent? What is cotangent? Isn't it 1 over tangent? So what is tangent times cotangent? 1. Because cotangent is 1 over tangent. So tangent times 1 over tangent, 1, right? Secant times cosine is 1. Cosecant times sine is 1, right? These are not things you have to memorize. They're just things that, of course, they are. Maybe? If you say so, Jeff. All right. Anything else? So I'm not going to finish that out, but at least now you know how to attack that, right? Nothing else. Okay. All right. I'm little sus about that. There should be some questions because some of these get a little freaky, but okay. All right, I'll be optimistic. So this is what we did last time. We developed a formula for, let's use the freaky letters. And let's do it the full way out. If I had sine of alpha plus beta, let's do that first. Does anyone remember what that would be? Sine's the nice guy. Yeah, so it'll be, sine says, hey, cosine, let's take some turns. So I'll do alpha. You do beta. It's a plus, so I'll keep it a plus. And now I'll do beta, and you do alpha. So I'm going to write this. I'm going to write 4 equations in 2. Because if I just put a minus here, wouldn't that be a minus there, right? Okay. So here comes the first instance, I think, for you, where you're going to see a minus plus instead of a plus minus, and it actually means something. What about cosine? If I do plus. Cosine alpha, cosine beta. Cosine's an asshole. It says me. You got a plus? That's nice. Put a freaking minus, and then of course, I'm done. You go ahead, son. Right? Poor little sine's like, okay. So what if there was a minus here? There would be a plus there. Do you guys see that? So the plus or minus is actually very important in some things. If it's plus or minus versus minus plus, that actually means something. This plus goes with this minus. Do you guys see that? So I just wrote 4 identities, right? Okay. Maybe? And then we used these to create identities for these two. What is sine 2 theta? That's the nice one. You just got one thing to remember. Let's see if anybody remembers. 2 sine, cosine. Cosine again. Asshole, right? He's like, okay, cosine 2 theta. It's 3 things. And you better pick right. Oh, cosine, what the shit. Now again, I'm just trying to give you a way to remember this. So 1 is the one we talked about earlier, cosine squared minus sine squared. And then of course, cosine squared is 1 minus sine squared, which leads to 1 minus 2 sine squared. And sine squared is 1 minus cosine squared, so that leads to 2 cosine squared minus 1. And again, cosine's an asshole, so when it's his turn, he's first, and when it's sine's turn, he's last. Again, I'm just trying to give you a way to memorize these, because you do have to know these. You just have to know them. All right, maybe. So what I want to do now, okay, so let me do this. I'm going to erase this. This is basically what we did yesterday, and it was a lot of fun yesterday. If you missed out, watch the video. We had multiple giant triangles that we were doing shit with, right? For those of you that were here, you were on the edge of your seat the whole time. I know. What's going to happen next? But I want to focus on this guy for a minute. I'm going to erase all this. Now let me keep this up. Go ahead. So let me ask you something weird. What if I wanted to know what the cosine of 15 degrees? Why does that suck? If I would have asked you this on the quiz, what would you have done? Why would that be mean? Because that's definitely one we don't have memorized, right? What is that related to that we do have memorized? 30 degrees. Isn't it exactly half of one of the angles we have memorized? So, if only I would have asked cosine of twice that. Don't we have a formula that does that? So, if I use this formula, now let me ask you, there's three options for cosine 2 theta, yes? What's the only piece of information that I'm asked about? Cosine of 15. Do I care about sine at all? Do you guys see what I'm saying? Do I care about sine in this question? Is there anything about sine up here? Nope. So which option should I pick then? The last one, yes? So if I want to know the cosine of 15, this lets me figure out, use the cosine of 30. Stay with me, stay with me. I really want you guys to see this. I have a formula that if one side has theta, the other side has 2 theta. I'm being asked cosine of 15 degrees, because my teacher is like cosine, he's an asshole. I'd rather have cosine of 30. Okay, this equation lets you figure out, based on cosine of 30, I can solve for cosine of 15. So let's see what this will look like. Cosine 2 theta is 2 cosine squared theta minus 1. What's theta in this case? 15. So what's twice theta is 30. Can't I solve this for cosine of 15? I don't know if you guys see what's happening. Can't I solve this for cosine of 15 degrees? Right? Couldn't I just add 1? Let's do it. What is cosine of 30, by the way? Close to where it likes it. Say again? We're at 3 over 2. I'm going to add 1 to both sides. All right, I got to do 2 more things. 2 more things. Sorry? Yeah, divide by 2, right? Divide by 2. So I'm going to do, let's see if you guys are cool with this. I'm going to divide this by 2, and I'm going to divide this by 2. Do you see what I could do there? Do you see what I just did? Isn't that already cut in half? So if I cut it in half again, isn't it cut in fourths now? That's the quick way to divide by something when there's already a fraction there. You just put more shit on the bottom, right? Is everybody, right? I'm just solving like we always do. That's all I'm doing. So I get square root of 3 over 4 plus 1/2 equals cosine squared. And what's the last step? Take a square root. Do I, now, plus or minus? This is a good question. Don't I end up with cosine of 15? What quadrant is that in? So should it be positive or negative? Positive. So I'm going to choose the positive. Okay. Now, thankfully, I am going to show us a way to make this quicker, because this would suck if I had to do all this every time, right? But let's just do this once. So let me write what we got so far. We have cosine of 15 degrees equals the square root of the square root of 3 over 4 plus 1/2. Can't I combine these? How would I combine these? What do I have to get? Yeah. Multiply by 2, is right? Just LCD, right? So this is a big part of math. This is weird. Trig is new. This is brand new. Holy shit, but I'm just adding 2 fractions. Who cares? None of the other weird shit changes that, right? So I just need to get a 4 on the bottom. So now I got square root of 3 plus 2 over 4. What's the square root of 4? 2. And what's the square root of this? I have no freaking idea. So we got an exact value for the cosine of 15 degrees. That's crazy. Can somebody see, what if I wanted the cosine of 7.5 degrees? I'm not going to make you do it. Can you see how I could get an exact value? Because now I know cosine of 15. So I could do the whole thing again, where this is 15. Do you want to do that? No, I can understand that, but could we if we had to? Of course. Yes?
Where it says square root why is it plus 2? Just a, like, plus
Oh,
2.
here? Well, were you cool with it right here? And then all I did was I got an LCD. And then I could do rad 3 plus 2 over 4, right? Is that cool?
Yeah, but didn't you take a 2 from the denominator?
Take a, how do you mean, alright, take a 2 where, sorry, here?
Yeah.
Oh, I did the square root of 4,
Oh, okay.
which is 2. Yeah, yeah. I sure as all hell can't reduce these, right? Because it's involved in an addition problem. I can't do part of an addition problem. Okay, yes.
Wouldn't the square roots cancel? It's weird to have like square
Okay.
root of that and
I
square
love it,
root.
Riley. What you just said is perfect. Are we used to seeing square roots inside of square roots?
Oh.
Do they still, now, we're not used to it, but is there anything weird about that? There's not a damn thing weird about that. In fact, let's do this right now. Ask your calculator what the cosine of 15 degrees. I want to see someone go, hey, calculator. The average is almost dead. Poor little dude. Make sure you're in degrees. Oh, Jeebus. Okay, that's a little blurry. You could do it there. You can you do it? Yes, you can. Focus. Okay, so make sure you're in degrees. Cosine of 15. I get that, right? Now let's try to plug, let's try to plug that other side of the equation in and see if it's the same thing. That's what we're saying here, right? We just did something by hand that we really shouldn't be able to do by hand. So we're just checking our work. So let's try it. So how do I plug the other side in? I want the square root of the square root of 3 plus 2. No, Jeff. All right, this is a perfect example of how to check. So I want the 3 in the square root inside, right? I gotta get over so the 2 is not also in the square root. You gotta be careful, right? So it's a beautiful example. I did shit, I looked at my screen, and I said, oh, that's not what I want. And then I want to come out of there and divide that by 2, right? Let's see if I get the same thing. Yes. I like it. Which answer is exact? This one? Or that one? See, go ahead. Anybody? I saw one person give me an option. Which one is correct? On the board or on the screen? Which one's exact?
Decimal.
So that's what every student thinks. It's wrong, and I want you to understand why. Does that decimal stop there? So how could that be exact? Doesn't it go forever? This is the exact answer. If I try to calculate this, I will get an approximation. Of course, I really want you to understand. Do you analyze your own thinking? Do you understand why you thought that was the exact one? Because you're like, well, it's got all those decimals. It's exact. No, because that goes forever. That is an approximation. I really want you guys to see that. This is the exact answer. Yes?
This is the question I asked you the other week. Because I asked you what was like 15, 30, and like I was asking, like what there was an name between 30 degrees and 0.
Oh, I see. Yeah, exactly. So now we have a way to handle some of those, right?
Right.
We still can't handle like cosine of 11 degrees.
Right.
Right.
But it's like, it's really,
But now I can do 15, I can do 7.5, I can do every half angle of whatever, right? How would you do sine of 22.5 degrees? Can I do something similar to what I just did? And isn't that, what's twice 22.5? 45. All right, so. Let's come back. Let's truncate this work. This work is too much. The amount of work in this problem is too damn high. So let's truncate some of this work. All right, and the first step of this is going to be, well, okay, let's do that at the end, I think, okay. So I'm going to write this up here. Let's start with this one. So in algebra, if I want to develop a new equation, a new formula, that I can just plug stuff into, I just work with an old formula and solve for some other piece of it. So I want to solve for cosine theta, which is basically, it's what we did here, isn't it? Then we eventually solve for this, right? We're just going to do it once, and then I can plug shit into the answer I get. I don't have to do it every damn time. Just going to do it once and make a new formula. I put new in quotes because it's not new, it's just the same formula. So what's the first step to solve for cosine? Add 1. Come on, theta. And then divide by 2. Same way we did earlier. So let me put this over here. I'm going to put that here. Is that cool? Cosine squared theta equals, I'm going to put 1/2 cosine 2 theta plus 1. Is that all right? And then what do I do? Square root. The minute I do that, I better put plus or minus. Why did we not have to do that here? Because we knew what the angle was. And we know it's in quadrant 1. Here, do I know what the angle is? No clue. I don't know what this angle is. I don't know if it's positive or negative. So I got to keep that up there. I really want you to understand, we're doing every step we did over here, just without numbers now. So now I get cosine theta equals plus or minus, there's multiple ways to write this, so I might as well write it like, let's just do it like this. I can either write it like 1/2 or over 2, it doesn't matter. Now, there's one thing I want to change here. And let's see if you guys are cool with this. Real quick, let's do this. Here's the equation. This is true. What is cosine of x then? What's cosine of x? Using that, what would it be? Nothing major, right? Plus or minus square root. Cosine of 2x plus 1. Whoop-de-doo, right? Yeah, Jeff. So here's what I'm going to do. I'm going to make this a half angle formula, because that's what I want it to be. I want it to be a half angle formula. So what am I going to do? I don't know. I'm going to take this away because we don't need this anymore. Is everybody got that? Who wants it? Okay. Shit, I should have kept that on. Let's make this a theta. So let me ask you this. What if I put cosine of theta over 2? Wouldn't I just put a theta over 2 here?
Yeah.
And what's twice theta over 2?
Yeah.
Theta, right? So this will be plus or minus square root of cosine theta plus 1 over 2. Is that all right? I like it. And just to show you, yeah, what's bugging me. I'm used to the one being first. Same thing here if I do this. But that's just the way I'm used to seeing it. Notice there is a sign of theta over 2. So I can do a very similar thing. But, so again, how did we get to this? We started with cosine of twice an angle is 2 cosine squared minus 1. We started with that, didn't we? And then we solved it. Couldn't I do the whole thing, but for, what if I knew sine? Which option for the double angle formula has a sine in it? Just a sine. 1 minus 2 sine squared theta. So I think maybe you could trust me on this, so we don't do it again. If I solve this for sine, the same way we solved this for cosine, I end up here. I get this. Okay. Do you see why there's a minus there? Because now the sign is on the other side, it's negative. So eventually I'm gonna have to divide by a negative number. Maybe. So what I want you to realize, some of you guys will latch on to what I'm about to say. For a long time, I didn't have these memorized, but I do now just because I use them all the time. But I would just start, these formulas are just these formulas solved. That's all those are. So you could just memorize these and then make those as you need them. Or you could just memorize the half angle identities. It's up to you. Okay. Now, real quick. I should have done this in the middle of this, but that's okay, John. I don't even know if I have these up here, do I? I don't think so. Yeah, because these are kind of silly. But I'm going to show it to you since the book makes a big deal out of it. Yeah, okay. I don't have them up here. Stay with me for a second. Is everybody roughly okay with this? We'll do some more examples, yes?
So we have like cosine 2 theta, 1 minus 2 sine squared theta, or
Yes.
this is like sine.
Sorry?
So for cosine, like we have two values, like 2 cosine squared theta, 1 minus 2 sine squared theta.
What about it?
So for cosine 2 theta, we have like 2 answers, right?
No. We have 3. It's the third one I didn't write up here. Cosine squared minus sine squared. So remember, there are 3 right here. Cosine 2 theta is cosine squared minus sine squared, or it's 2 cosine squared minus 1, or it's 1 minus 2 sine squared. And again, that kind of falls into the cosine is a jerk idea. Sine of 2 theta, just one thing. It's like, I got you, just one thing. Cosine is like, screw you, human. Memorize 3 things. Yes. Oh God, thanks, cosine. And again, hopefully you guys understand. I'm just trying to give you a way to remember this. Maybe, I don't know. Okay. Because you have to memorize these. Right? I think I made that point. Okay. One little thing that we could have done in the middle of this process. So,
I have a quick question
Oh,
about
sorry.
this.
Yeah.
So with those 3 different identities for
Yeah.
2 cosine,
Yeah.
if you divide by 2 with all of them, you'll end up with the half identities?
Not that easy. No. And this one, of course, doesn't really help. I only want to use these 2 because I only want to, if I have a question about cosine of 15 or sine of 15, I don't need both of them at once. So that's why we chose this one and we chose this one. Is that cool? Now this one is still useful, it just doesn't lead to something good for half angle. Okay. Okay. There's one little thing, so let me see if I can do this really quickly. I sort of start to solve this, add 1, divide by 2, right? Isn't this cosine squared? Let me see. So if I add 1, divide by 2, don't I get cosine squared is this? So if I'm in a situation where I need to rewrite cosine squared in terms of cosine, I would use this. Let's see if you guys understand why this is given the name it is. This is called a power reducing formula. What's the power on this side? Second power. What's the power on this side? So it reduces the power, right? There are situations where it's easier to work with a first power cosine than a squared. In fact, it is primarily immediately in calculus, for example. And of course, this is called pre-calculus, so that's why we talk about this shit, because it's going to help us a lot in calculus. There's a calculus thing you do where this would suck. In fact, this would be almost impossible, but this is easy. So I want to be able to write a squared in terms of a first power. It's kind of neat. It's power reduction. So if I have a square on my trig, I can write it in terms of a first power. The trade-off is the angle doubles. Maybe? And you get a similar one for sine. And you can kind of see it because it's just basically squaring this. So you get 1 minus cosine 2 theta over 2. Okay. So those are called the power reduction formulas. I didn't even put them on here because they're just basically these, not taking the square root. That's all they are. Maybe. So this is about where students very often sort of become a little disconnected, right? What are trig functions based on, again? What about right triangles?
The relationships between the sides.
Yeah, the sides. So trig functions are based on ratios of sides of right triangles. That's all they ever are. But from yesterday's work, you can start to see how I can have right triangles inside of right triangles. I could do a lot of shit. All the trig functions are is ratios of sides. That's all they are. But once I have multiple things happening, I can make really complicated relationships. But they still are just ratios of sides of right triangles. That's all they are. But then you get to this point, and you're like, I don't see the right triangle anymore, Jeff. Well, this is after a lot of manipulation of stuff. Maybe.
Is that with like multiple triangles?
Say again?
Is that with multiple triangles? The sine square? Is that when you start using it?
Oh, no. This could show up anytime it wants to. There are multiple situations where this is used to model something happening in real life, right?
Okay.
There's a lot of ways to answer sort of your question. I mean, this can show up anytime it needs to. So we have to know how to work with it, right? Okay. All right. Okay. So that's those. That basically closes out section 9. What was it, Jeff? 9.2 or 9.3? Let me see. All right, let's see where we are. Whee! All right, just to show you. Yeah, I got it. Trig identities, we did those. Sum and difference stuff, we did those yesterday. Double angle, half angle, reduction formulas, we did today. I don't know if you guys remember 9.4, I made it extra credit. Those are more obscure identities, and just to show you them on this sheet, that would be these guys. Those don't come up as often. So if you're in calculus and you need to know one of these things, you just kind of look it up. It comes up not very often. Whereas these come up so often, you need to know them. So you don't have to constantly look them up. I don't know if you guys are with me. So that's why I felt comfortable making section 9.4 extra credit. Right, so it's 9.4. If you remember on the new homework sheet, 9.4 is extra credit. Okay. So now we're going to do, finally, Anytime we learn a new function, we want to see what does it work like in an equation. So now we're going to do trig equations, which I'm sure everybody's like, oh, good. So let's see what happens with these. There's one more thing. All right, it'll come back to me. Shoot. All right, let's actually, let's do this. I want to immediately show you. So I'm going to start with a very nice basic equation, but I want to show you how to write the answer because, let me ask you this. If my equation was cosine x equals 1/2, I don't actually have to solve this. I could just reason it out. Do you understand what I'm saying? Like, this is asking what angle gives me a cosine of 1/2. Can't we just figure out what that is? Does anyone know what it is? Well, I'm gonna love that. So you gave it to me in radians. I love it. We're gonna mostly use radians. Is everybody cool with that? So if you think degrees, cosine of 60 is far away from where it likes it, so it's scared, so it's 1/2. So that's pi over 3. Now, can anyone tell me, that answer is correct, but it's not complete? The answer is correct, but it's not complete. So, you can give me one other answer at least immediately. So at 60 degrees, at pi over 3, the cosine is 1/2. Can't you think of a reference angle to put me somewhere else where the cosine is still 1/2? Where's cosine positive? Where's cosine positive? Which quadrants? First and? Fourth. So is there another place where cosine is 1/2? Yeah, so it'd be, and remember, let's use some radians here, so this will be a little bit tricky. But isn't there one here where the cosine is also 1/2 and is actually the exact same 1/2, isn't it? Do you guys see that? But now the angle is back pi over 3. Say again? 5 pi over 3, I love it. All right, so this is 0 radians, right? What else is it also known as? 2 pi radians, correct? So if I go back pi over 3 from 2 pi, okay. 2 pi is 6 pi over 3, right? 6 pi over 3 minus pi over 3, 5 pi over 3. 11. Stop for a minute. Do you guys understand there's at least that answer also, isn't there? So pi over 3 is not complete. So then you add 5 pi over 3 to the answer, right? All right, and I'm going to say to you, you're still not done. How many answers are there to this equation? Infinite. Right? If I go pi over 3, I get cosine is 1/2, don't I? If I add how much to it? What do I add to it to come all the way back around to that? 2 pi. And then can't I add 4 pi? And then can't I add 6 pi, right? You guys with me? Could I also subtract 2 pi? Subtract 4 pi. We know this. We know that trig, since it just repeats and repeats and repeats, it keeps giving the same answers forever. So there must be an infinite number of answers to this. So, watch this. This is how we write this. One set of answers is going to be based on this. The other is going to be based on this. I think the book does plus or minus. I can't remember. I'll check it later. I normally don't do plus or minus, but we can do that. So remind me, if I have one answer, don't I go through a full rotation to come back to that same answer again, right? So when I add 2 pi, 6 pi, 5 pi over 3, 2 pi over 3, 5 pi over 3, I love it. 2 pi is 6 pi over 3, right? 2 pi is 6 pi over 3, 5 pi over 3. I love it. 2 pi is 6 pi over 3, 5 pi over 3, 2 pi is 6 pi over 3, 5 pi over 3, 2 pi is 6 pi over 3, 5 pi over 3, 2 pi is 6 pi over 3, 5 pi over 3, 2 pi is 6 pi over 3, 5 pi over 3, 2 pi is 6 pi over 3, 5 pi over 3, 2 pi is 6 pi over 3, 5 pi over 3, 2 pi is 6 pi over 3, 5 pi over 3, 2 pi is 6 pi over 3, 5 pi over 3, 2 pi is 6 pi over 3, 5 pi over 3, 2 pi is 6 pi over 3, 5 pi over 3, 2 pi is 6 pi over 3, 5 pi or subtract 2 pi, correct? But that still doesn't give me every answer, because can't I add multiple 2 pi's? Just keep rotating, keep rotating. So what we do, I can't remember this book, there's a couple things you gotta look up in this book. I'm used to using a K here. I can't remember if they use an N. Shit. Every book is a little different. Marv. Yeah, they use a K, good, I like it. I really want this to make sense. All this is saying is, I know the answer is here. How do I get here? I can turn pi over 3. I can turn another 2 pi after that. I can turn another 2 pi. Or I can turn back. This is all the same. Go, keep turning in the positive direction by a multiple of 2 pi. Or go backwards, a multiple of 2 pi. That's all that says. So don't I have to do that with the other answer? So these two answers are the basic answers. They're like within one rotation. They're the pi over 3, the 5 pi over 3. Those are the ones I think of immediately. But then I have to add and subtract multiples of 2 pi. If I do a rotation, don't I end up in the same place? Isn't that still another answer, right? I really want that to make sense.
Does it matter if the pi and the k is in front of each other?
It doesn't matter. How did they do it? Oh, they put the k. I like to do this because then it's a multiple of 2 pi. But this is all 2 times pi times k, so it doesn't really matter what order it's in. Yeah, so the book likes to put their k in the middle, apparently. They're weird like that. Okay, maybe. Okay, that's the first thing to realize. So let's do this problem again with one extra instruction. So this is this problem, this is the answer. This is the answer to this problem. So what if I gave you the same problem, but I gave you one more thing? What if I say solve this, but x is in 0 to 2 pi. So now I've restricted my domain. Am I going to have an infinite number of answers now? No, I'm only allowed to go through one rotation. I can't do multiple rotations. So now I'm only going to have 2 answers. The basic 2 answers we got. Pi over 3, 5 pi over 3. Done. You are going to see both of these types of questions in this section.
So all the answers, or you just want to see answers?
Yeah, it's either an infinite number of answers, so you have to do some kind of plus or minus something,
Right.
or they'll tell you, oh, you're only within 0 to 2. Okay, so then you don't have to worry about the plus minus, you just have to get the ones that work within one shot of the unit circle, right? Okay.
So what would 4 pi look like?
What do you mean? Sorry. Okay, good question. All right. Because that sort of could happen. If it says 0 to 4 pi, that's your question, right? So it'd be pi over 3, 5 pi over 3, add 2 pi to this, right? Again, it's the same idea, except I don't do infinite multiples of 2 pi. I just do 2 pi. I really want this to make sense. If this angle is an answer, and it is, isn't plus 2 pi to that, isn't that also an answer?
Yeah.
Okay, so what's pi over 3 plus 2 pi? Seven pi over 3, right? And I also add 2 pi to this. Or actually, 2 pi over 3. So if this is an answer, so is that. Right? So what's 5 pi over 3 plus 2 pi? Maybe? So that's a good question, I like it. You'll get something related to that. You normally don't get a problem that says this specifically, but there will be a situation kind of related to this, so I like that question. Maybe. All right, so let's try a harder equation. Or a different equation, let's do that. Yeah, let's do this, not too crazy yet. So what about tangent x equals -1? So this really, the more you know your basic trig values, the better you are with inverse trig. And the better you are with inverse trig, the better you are at this. You just gotta think. Well, first off, what quadrants would we be in for tangent to be negative? Quadrant 2? And 4, right? Is that cool? Tangent's negative when sine and cosine are opposite signs. Does that make sense? Because tangent sine over cosine? So sine and cosine are opposite signs here, and they're opposite signs here. And again, why is that? Cosine likes x, sine likes y. So where are x and y different sides? Okay. Say again? Oh, it's interesting you say that, because it doesn't have anything to do with the answer, but it does have something to do with the process, sort of. I don't care about the rad 2 over 2, because I'm not asking sine or cosine. What's the angle? When is tangent some kind of 1? Say again? Nope. Yeah, tangent's going to be 1. Okay, guys. Okay. Tangent is sine divided by cosine, right? Tangent's going to be 1 or -1 when sine and cosine are the same. When are sine and cosine the same? Pi over 4 stuff, right? Now the answer is not pi over 4. Why not? Because pi over 4 is in the first quadrant. Tangent would be positive, right? So what's in the second quadrant?
3 pi over 4?
Yes, 3 pi over 4. So that would be a reference angle of pi over 4. That would be 3 pi over 4. What's in the fourth quadrant?
7 pi over 4?
7 pi over 4. I love it. And again, some of you guys, you know this is 2 pi. You know that's 2 pi. So if I want to be pi over 4 before that, 2 pi minus 1/4 of a pi. So 8 pi over 4 minus pi over 4 is 7 pi over 4. Now let me ask you this. Okay, stay with me now. Okay. I could do the same thing. In fact, did I give us any restriction on what the answers could be?
No.
How many answers should I get then?
Okay.
Infinite answers. This tangent's interesting. Okay, watch this. I could certainly do add 2 pi and come back to here, correct? So let me do this slightly wrong, and then I'll show you the right way to do it. So couldn't I just do exactly like we did before, plus or minus 2 pi k? Right? Exactly the same reason as before. If I have an answer and I rotate fully, I come right back to that same place, don't I? And I can do the same thing backwards. So what would I put here? Plus or minus 2 pi k. Two things. I don't have to do that, and this is sort of wrong. This is correct. These are the right answers. It's just more that I need. How far apart is pi over 4 and 7 pi over 4? Pi. So if I go pi and then go another pi, don't I pick up each answer over and over? I really want this to make sense. So I don't have to write this like this. I can start at 3 pi over 4, and if I add or subtract pi, don't I get the other answer too?
Yeah.
And then if I add or subtract pi again, I get the other answer, and so forth. So if I just do that forever, I get all the answers. Why does this make sense? What's the period of sine and cosine? Shoot, I don't have it up here. What's the period of sine and cosine? 2 pi. Remember when we did the cosine problem, didn't have to do plus or minus 2 pi k? What's the period of tangent? Pi, right? So I should be able to write my tangent answers with plus or minus pi k when I need to, right? And the sine and cosine answers would most of the time be plus or minus 2 pi, because that's how long it takes for it to come back to the same place. Maybe. So if you do this, you're technically not wrong. It's just convention to write it with one statement instead. Now, I can feel that some of you guys aren't really quite getting this. Why couldn't I do that with, remember the earlier answer we got was pi over 3 and 5 pi over 3? How far apart, how far do I have to go to get from here to there? I'm at pi over 3, what do I add to get to 5 pi over 3? If I'm at pi over 3, what do I add to get to 5 pi over 3? If I'm at 1 pi over 3, what do I add to get to 5 pi over 3? 4 pi over 3. Stay with me. If I add pi over 3, don't I get to here? And if I add another pi over 3, don't I get to there? So aren't these plus 2 pi over 3? Some of you guys are going to get this. Do you see how these pi, right? So much pi. These plus 4 pi over 3, plus 2 pi, plus 4 pi over 3, plus 2 pi. I can't consolidate those because they're not equally spaced. That's why I needed 2 rows of answers for this one. Whereas this, pi, I can do it in 1. Maybe. So again, this is something we knew about trig functions from almost the beginning. They have infinite answers. They have infinite times there at certain answers. Because I can just rotate forever and go crazy. Right? So the answers to trig functions should have that infinite idea in them, unless they tell me, oh yeah, only do 0 to 2 pi. Some problems will do one of those two things. So you have to be careful. Okay. All right, let's step it up. So those are 2 basic ones about tangent and cosine. Let's get some funkier stuff happening. Let's see, what about, sine squared x equals, 1x. I need to solve this. Does anyone have a suggestion as to a first step? Can't do an inverse sine because I don't have a sine. I have a sine squared. So what's the first thing I should do? Square root. Oh shit, plus or minus, right? Always. Whenever you take a square root, it's gotta be plus or minus. You guys really understand why that's true? You're all like, I'll just say I do, because I don't want to, okay. So I always have to put plus or minus when you're the one taking the square root. So I get sine. 1 over rad 2, I can rationalize that to be rad 2 over 2. Does that sound, and it's plus or minus, does that sound like a familiar value? Anybody? Rad 2 over 2, does that sound like a familiar value? What angle does that relate to fundamentally? Sorry. 45 degrees, okay, which is in radians what? 5 or 4. Okay, we're not done. I'm gonna write that down because I know that's for sure, right? Now it says, so where else, now notice, this is plus or minus. So I'm gonna, which 45 degrees, which quadrants could the answer be in? All of them. Because sine could be positive or negative. Isn't sine positive here and here, right? But it could be negative, right? Where's it negative?
3 and 4.
5 pi over 4, right? 7 pi over 4. Okay, so let's write those down real quick. So if the problem said between 0 and 2 pi, these would be my answers. My answers would be pi over 4, 3 pi over 4. That's when it's positive. 5 pi over 4, 7 pi over 4. That's when it's negative. But do I say only live within 0 to 2 pi? Do I say that? No. So there should be an infinite number of answers. Now. I really want you guys, wait a minute. The period of sine is 2 pi. So it seems like there should be plus or minus 2 pi k going on, just like we did before with the cosine. Do I have to do that though? Let's start at the first answer. How far do I go from this first answer to this answer? From pi over 4 to 3 pi over 4. From pi over 4 to 3 pi over 4. How far is that? Yeah, 2 pi over 4, pi over 2. I love it. So this is plus pi over 2, right? How far is this from the next answer? Pi over 2 again. Pi over 2 again. Pi over 2 again, right? So I can catch, I really want this to make sense. If I start at pi over 4, I can catch every answer by just adding a multiple of pi over 2. I can just catch them all, right? So I could do the infinite solutions to this, I can do in one statement. If I start at pi over 4 and I add or subtract pi over 2, as many times as I want to, I'm going to end up at one of these positions forever and ever and ever and ever and ever. I could have done pi over 4 plus or minus 2 pi k, 3 pi over 4 plus or minus 2 pi k, 5 pi over 4 plus or minus 2 pi, oh my god, right? I could have done that, but visually, I see I don't need to because they're all equally spaced. I can catch them in one statement. And again, that very first problem we did, were the answers equally spaced from each other? No. They weren't. I had to go 4 pi over 3, and then I had to go 2 pi over 3. I couldn't catch them in one statement. That's why I had to use two statements. I'm leaking students out of the class, but we're not done yet. Okay. So far, the equations have been too easy. Says you, Jeff. Say again? Same thing.
Okay.
Same thing. What about if it's this though? I don't know what number I'm on, so I'm just gonna put example. You're kind of dying. Let's see. Yeah, let's do this. Sine of 3 theta equals negative rad 3 over 2. Oh, shit. Let me ask you real quick. If I just said sine x equals negative rad 3 over 2, could you give me some answers for what x is? Where is sine negative rad 3 over 2? Which quadrants are we in? Third and fourth, because that's where sine is negative, so y is negative. So where is it, what reference angle gives me rad 3 over 2 for sine? So it's got to be closer to 90. Oh, it's not 4, because that would be rad 2 over 2, right? Pi over 4 gives you rad 2 over 2. What gives you rad 3 over 2? Closer to the y-axis. 60, right? Pi over 3. Oh, okay, I'm sorry. I misheard you. So if I want to be in the third quadrant, that would be 4 pi over 3, right? Because I want to go pi over 3 in. And the fourth quadrant would be 7.
No, wait,
No, no.
5.
5 pi over 3. Because you want to be pi over 3 back from 2 pi. Again, some of you guys might start to realize, what is 2 pi also known as? Isn't it also known as 6 pi over 3? So if I'm pi over 3 back from it, aren't I just at 5 pi over 3? Not a big deal. So you need to start thinking about 2 pi as, it could be 4 pi over 2, 3 pi, 6 pi over 3, it could be whatever you need. 12 pi over 6, right? Okay. Do I have x here?
Yeah.
No, but I do know that whatever the shit 3 theta is, I know what it's equal to. Sine of stuff is this. Stuff is 4 pi over 3, or stuff is 5 pi over 3. So I kind of ignore the fact that there's a 3 there at first. I just look at this like an angle. So angle equals this, or angle equals that. Now, have I got all the answers yet?
No.
Are these equally spaced from each other?
No.
Whoa. Whoa. No, I can't. So I can't consolidate them. I have to use 2 separate lines. So starting here, I can go add 2 pi, or subtract 2 pi, subtract. So this would be plus or minus 2 pi k. And the same thing here for the exact same reason. Now, what do you think you do? I haven't solved for the variable yet, have I? I know what 3 times the variable is. So how do I figure out what the variable is? Divide by 3. So this will be 4 pi over 9. You guys see that? If I divide by 3, aren't I dividing this by 9 now?
Right.
Plus or minus 2 pi k over 3. And then the same thing here, divide by 3. 5 pi over 9, plus or minus 2 pi k over 3.
So, you just find the angle.
You find what I call the base angles.
Right.
Within 0 to 2 pi. And then you build all the other answers off of that, right? Generally, you're going to put plus or minus 2 pi k. Sometimes you don't have to because all the answers are equally spaced from each other. You can actually capture them all in one line. Maybe. Weird shit, brand new shit. I understand. All right. So here, you guys, I'm going to give you one to try on your own. I'll give you one that's not too crazy. Try on your own here. Let's see. So what do we just do? Sure. Sine x equals -1/2. let's do that. So if you think, again, what quadrants will we be in? 3 and 4. Same reason as the last problem, the sign is negative. What's the reference angle that makes it 1/2?
7, 5, or 6.
Well, the reference angle,
Oh,
5 or 6, I'm with you.
right.
But, so now if I'm in the third quadrant, 7, 5, or 6, I like it. And the other possibility. So again, if you think of 2 pi, that is 12 pi over 6, correct?
Right.
So 12 pi over 6 minus pi over 6, 11 pi over 6. Now these are not equally spaced again. Long, short, long. So I'm going to need 2 separate lines. Yeah, plus or minus 2 pi. That was a nice one. Okay. All right, so here, what about this one? Yeah, I like that. Let's see, do I want it to be 0? No, let's make it, no, that's fine. There's 2 ways to do this. I want to do it the second way. All right, so the first way would be subtract 1, divide by -2, take a square root, plus or minus, blah, blah, blah.
Yeah.
Boring shit. Do something a little better. What is 1 minus 2 sine squared theta? Does that look familiar to anybody? Cosine is something. Cosine 2 theta. This would be cosine 2 theta equals 0. So what angle makes cosine 0? Yes, good. So either pi over 2 or negative pi over 2, also known as 3 pi over 2. Notice these 2 answers, aren't they separated by, what are they both separated by from each other? Pi, aren't they just pi apart? So I can catch all the answers in a single line because they're equally spaced. If I just keep adding pi, I'll get one set of answers, the other set of answers, one set of answers, the other set of answers, because they're equally spaced. So I would add multiples of what? Pi. Multiples of pi. So then what's the answer? Divide by 2, right? So it'll be pi over 4. Oh, sorry, plus or minus pi over 2k. Same answer you would get if you added 2 sine squared, divided by 2, took a square root, blah, blah, blah. Real quick, I just want to show you real quick. Isn't this fundamentally 45-degree angles, right? If I were to solve this the other way, so add 2 sine squared, divide by 2, I'm just going to check around, take a square root, which I can do this 2. Where is sine theta rad 2 over 2? Oh, plus or minus, well, not here. Here, plus or minus, plus or minus. Where's sine theta rad 2 over 2? Pi over 4, 45 degrees, right? 45 degrees. And then, of course, I can just pick up all the answers plus in the same way. So I would get the same answer. It's up to you which way you go, right? So trig identities could come into play when you're solving these kind of equations. Okay. All right, last example, I think, and then I'll let us out a little early. Maybe, when we think about it. I might want to do one more thing. All right, let's see. I gotta think for a second. Let's see. Do it alive. Okay. So what if I had 2 sine squared theta minus 3 sine theta plus 1 equals 0. Aw, shit.
Oh, no.
What do you do? Let me show you, this is an option if you want. Do you know what sine theta is? No, right? That's the whole point, right? This is an option if you want to. You don't have to do what I'm about to do, but it's an option. Let me see. So if I don't know what sine theta is, so let's call it x. You guys with me? I don't know what it is. So what's x squared? Sine squared. So how can I rewrite this now? 2 x squared minus 3 x plus 1 equals, how do you solve that? It's quadratic. It just didn't look like it because sine was kind of like in my way. All right, this is easy because that's 2x and x. This is 1 and 1, and now they both have to be, no, got to be positive ones. They have to have the same sign, they have to be negative, so they both have to be negative. Is that cool? Not many factors of 2, not many factors of 1, so that was relatively easy. So then either 2x minus 1 is 0, or x minus 1 is 0, right? Right? So x is 1/2, or x is 1. Do I just circle that and say I'm done?
No.
What was x?
Sine.
Sine theta. So now sine theta equals 1/2, or sine theta equals 1. So when is sine theta 1/2? Pi over 6, or? Yeah, either pi over 6 or 5 pi over 6. And then you can do our little plus or minus 2 pi k. When is sine theta 1? Pi over 2, plus or minus 2 pi k. So then I get all of those. So it's quadratic. I broke it up into 2 linear functions, and then I got answers for both. So that you're going to see in the homework.
So it's like,
Say again, sorry?
so it's like really like a quadratic, you just, like focus it real quick and bring it up?
I'm sorry, do it.
Like how you just did it, can we do that? With the 3C, it come up like that?
Oh, hell yeah, of course. That would be really evil for me to go, isn't that nice? You can't do this. So, this is, this idea of substituting for part of what I'm looking at
Right.
is done a lot in mathematics. In calculus, we do something called U substitution, where we replace something with U and it makes everything look prettier, makes it easier, and then we just plug back in
What was supposed to be?
what it was, and then we can finish it out. So it makes the middle stuff easier, right? Okay. Okay. So one last thing, and then I'll let us out. A little preview of what we're about to do. If I had a triangle that was not a right triangle, so I have angle A, angle B, angle C, side, C is an evil letter, C, side A, side B. It seems like I shouldn't be able to use trig functions to do much anything. In fact, does Pythagorean theorem apply here? It doesn't seem like it should, right? All right, we're not going to do anything today. I want to tell you what we're about to get into. We're about to get into how could I extend the idea of trig functions to include non-right triangles. Can't I find right triangles in here? Can't I do that and find right triangles? Yes? No? Screw you, Jeff? Okay. So I should be able to kind of like manipulate some things and use trig, even if the triangle I am working with itself is not right. It's not right in the head. No, it's not 90 degrees. And this only works for right triangles, correct? But this isn't even the full form. There is something where I subtract something, and then it works for every triangle everywhere. No matter if it's right, not right, whatever. So we're going to start to get into, in fact, it's related to that, a couple things that are on that green sheet, the trig identities. So we're going to kind of finish out that stuff. We're going to actually talk about the last two things. They're called law of sines and law of cosines. And these are freaking cool as shit, right? The first time I learned this, it blew my mind that this is a specific situation. If this is not a right angle, there's just an extra piece that shows up. And it's really neat. So then I can use Pythagorean theorem basically on any triangle. It doesn't have to be a right triangle. It's crazy. All right, that's a very small preview. That's what we're going to get into next. Okay. The next test is next Thursday. It's next. It's Tuesday, the 22nd, I believe. Somebody correct me if I'm wrong. That's the next test. So next week, the 17th will be review day, right? And the test doesn't go through the whole next chapter. It stops at section 10.3, I think it is. So let's do a quiz on, I know we just had one today. I don't care, that was old news. Quiz on Tuesday on section 8.3, and I believe I just want to do 9.1. I believe that's that. Make sure that was what it is. Yeah, let's just do 9.1. So that's next week on Tuesday. We'll have a quiz on those. Okay, that's it. So I'll see you guys next week.